Hello, everyone, and welcome back to another edition of zkStudyClub. This week, we are excited to welcome some of the authors of Reef, which is a new paper out on fast, succinct, non-interactive zero-knowledge regex proofs, not to be confused with regex proofs, which are not a thing, regex proofs. And yeah, we have Leff, Eli, and Jess here, three of the five co-authors of this paper. Which also includes Srinath, who's been a presenter on zkStudyClub a couple of times. And yeah, pretty excited about this one because this kind of describes, I think, a little bit more application-oriented use case for zk. And so with that, I'll pass it over to you all. Thank you very much for being here. The floor is yours.
Awesome. Thank you so much. So since Alex introduced us, again, I'm Eli, and I'm here with my collaborators, Leff and Jess. And today we're going to talk about Reef. So when we talk about zero-knowledge regular expression proofs, we're talking about matching a public regex against a private document. So why is this something we even care about? Well, it turns out there's a lot of applications for something like this across a variety of domains. So in something like system and network security, you might have network administrators who want to enforce a DNS block list, while users of the network might want the privacy afforded to them by oblivious DNS over HTTPS. Alternatively, you might have users using a protocol called APAKE, which allows them to register and authenticate to a server without having to provide their password. But if this is in a corporate or institutional setting, the server might want some guarantee that the user has a password that's better than 12345. Alternatively, users might want spam keyword filtering while not having to show the entire contents of their email to Google or Proton Mail or whoever. In the realm of justice and journalism, you might want to prove things about redacted government documents, which are the results of FOIA or Freedom of Information Act requests. And then finally, in the case of biology and personalized medicine, individuals might want to prove certain things about their genetic code, like genetic mutations to personalized drug treatments, without having to provide all of their DNA to a big pharma company. And this last use case is the one we're going to talk the most about today, but we examine all of these in the paper. So let's think about a clinical trial setting. Vicky is running a clinical trial, and she's looking for participants to her trial with a very specific genetic mutation. She can actually represent that mutation with a regular expression. And let's say that Patty has the correct genetic mutation and would like to participate in the trial. One approach to this is Patty registers online, and as long as there's space, is automatically accepted and enrolled in the trial. Of course, with this approach, though, Vicky can't confirm that Patty actually meets any specific set of participation criteria. And this isn't what happens in the real world. In the real world, we have Patty send Vicky her DNA in the clear. Vicky then confirms that Patty has the correct genetic mutation and can make a decision about whether or not to enroll her in the clinical trial. But the problem here is that Vicky has Patty's DNA in plain text, even if Patty isn't ultimately accepted into the clinical trial. So we want to prove that Patty qualifies for Vicky's trial, meaning her genetic code matches the regular expression of the mutation Vicky is looking for, without Vicky learning Patty's DNA before she's been enrolled. We're all here today because obviously we can do this with zero-knowledge proofs. With a zero-knowledge proof, Patty can register for Vicky's trial and attach a proof that she qualifies, meaning a proof that her genetic code matches the regex of the variant that Vicky is looking for. Vicky can then verify this proof and decide whether or not she wants to enroll Patty in the trial. But because we do this in zero knowledge, Vicky only learns if Patty qualifies for her trial. If she decides not to enroll Patty in the trial, Vicky learns nothing else about Patty's DNA. So we can do this in 4 easy steps. So first, Vicky expresses her regex matching statement as a circuit satisfiability instance. Vicky publishes her circuit. Patty finds a satisfying witness, and Patty proves to Vicky that she knows the satisfying witness. When we talk about Reef, we're mostly focusing on this first step. How do we express regex matching statements as circuit satisfiability instances? And in particular, we focus on how do we express these matching statements as rank 1 constraint systems. So we're going to talk a lot about R1CS and R1CS constraints throughout the rest of the talk. So right off the bat, you might have an intuition for how we could do this. We can take a regex. Here we have A plus B dot star. So match strings with more than one A, followed by a single B, followed by anything any number of times. And so you might remember all the way back from your intro to theory classes that we can represent all regular expressions as non-deterministic finite automata. These are defined by a set of states, Q, an alphabet, sigma, a transition function, delta, which tells us, given a state and a character, how do we move to the next state? Where do we go next? We have a set of start states and a set of accepting states. So let's consider what it would take to express this as an arithmetic circuit. The biggest part of our automata is that delta, that transition function. And naively, we could represent this with a series of cascading if statements. If you're in state 0 and you see an A, move to state 1. If you're in state 0 and you see a B, stay on state 0, etc., etc. We would then do this for every single character in the document, processing a character and a state one at a time. We could write this up in your favorite, zero knowledge proof language, Circom, Socrates, take your pick, and generate an arithmetic circuit. Cool. So why are we here? Well, it turns out there's a couple of problems with this approach. The first is that of regex expressiveness. While it's true that non-deterministic finite automata can be used to express any regular expression in formal language theory, what it means to be a regular expression has really expanded over the past 20, 30 years to include things like this. This includes something called a look-ahead. Specifically, look-aheads are a type of structure in regular expressions. There are also look-behinds. They're collectively referred to as look-arounds. And essentially what this regular expression is saying is 3 conditions need to be met by my string. It has to contain an A, it has to contain a B, and it has to be between 2 and 6 characters long. Unfortunately, NFAs are really bad at expressing these, and lookarounds in general result in a pretty significant state explosion. So that's not great. The second problem is with our delta function and iterating through it once for every single character in the document. In a sort of normal zero knowledge proof system, this requires unfolding the for loop, right? Representing delta in the circuit once for every time we plan on calling it, which is pretty expensive. But maybe if the delta function is cheap, it's not an issue. But that's not the case. If we represent this delta function as a series of cascading if statements, this requires size of alphabet times size of automata if statements, which comes out to, big O of size of alphabet times size of automata constraints. So if you're keeping track at home, this naive solution requires size of document times size of alphabet times size of automata constraints. That's bad for large documents, like Patty with her DNA. It's bad for large alphabets, like ASCII or Unicode. And it's bad for large automata, like those that result from regexes with lookarounds. So Reef addresses each of these in turn with 3 key insights. The first insight is the introduction of something we call skipping alternating finite automata, or SAFAs. So alternating finite automata already exist in the literature. They've existed since the 90s. And they allow us to express lookarounds much more succinctly than traditional non-deterministic finite automata. We then extend AFAs to create a new class of automata that allow us to skip over irrelevant parts of the document. Second, we replace that series of cascading if statements with start state, character, end state lookup arguments in the circuit. And then finally, we make all of this much more performant by using a recursive proof system. Through these 3 key insights, Reef is able to decouple prover running time from document size in a way that previous works haven't been able to. So at a very high level, Reef works as follows. Patty commits to her DNA using a commitment scheme that is hiding and binding. Vicky publishes a regex of the genetic variant required to participate in her trial. Patty proves in zero knowledge that her committed DNA matches the public regular expression. Because we use a commitment scheme that is hiding, and we do this in zero knowledge, Vicky learns nothing except whether or not Patty's DNA matches the regular expression. Vicky then verifies Patty's proof. So we're going to talk about each of those three key insights and components of Reef, the SAFA, the lookup arguments, and the use of recursive proof systems. We're also going to talk about some additional optimizations we implemented to make Reef much more performant. And then finally, we're going to talk about how we evaluated Reef and how it compares to other existing systems. And with that, I'm going to hand it over to Lef.
Yeah, so the key observation that we made is that the regular expressions we want to match are sparse. So that means a really big document and really small regular expression. It's possible to match because it has a lot of wildcards that kind of capture the biggest part of the document. In the existing automata in the literature, wildcards like the ones you see here at the end of the string are kind of matched the same way as characters. We introduced, so in AFAs, for example, as you see here on the left, there's two types of states. There is the existential quantifiers. So this corresponds to the NFA, the existing NFA states, right? You get a choice between characters A or B. And we add another type of state, which is the universal quantifier state. And this is a bit different. This means that every child coming off of that state must match the rest of the string. So if we look at the regex and look at this AFA diagram, we can sort of see that the left-hand child corresponds to the left look ahead, the middle to the middle look ahead, and the right-hand child, which is a really long kind of chain of wildcards, corresponds to the rightmost regex, the 2 to 6 wildcard. But if we were to match the right child, right, we would have to do all those transitions. Well, we don't really need to check the characters underneath because they're wildcards. All we need to know is that we can skip over that region, and that's kind of the intuition for skipping alternating finite automata. We replace these long wildcard regions with a labeled edge. We label the edges with skip, and then we provide sort of a set of intervals which says by how much are we allowed to skip the cursor at that point. We also have a skip with an asterisk, which says that you can pick basically any future cursor to fast forward to. And then we, of course, maintain the normal edges with characters from NFAs and AFAs. So in order to see SAFAs in action, we'll go through an example. So the same regex as the one we had before compiles to the same SAFA. And let's take the string. You see the string is indexed. The second row is the indices of each letter. And we start at position 0 and with a cursor at position 1. So this is a universally quantified state. So as I said, all children must match. So this is a logical end. So I will take all transitions, and these are skip transitions. So that means I can basically come up with a cursor to fast forward to. On the leftmost child, I have a star skip, so I can pick any cursor. In this case, it's convenient to pick the same, c equals 1, because really we know that the A that we're looking for in the next step is at position 1. And the second one, we pick cursor 2, because that's where the B is at. And the third one, we don't really care. We can pick any cursor as long as it's between the 2 to 6 interval. The most convenient one is to just fast forward to the end of the string, the cursor number 6, and accept. So that's done. What about the other two? Let's see. So we start at state 1 at cursor at position 1. We consume the A, which is at cursor position 1. And that puts us in, that bumps the cursor by 1, and that puts us in state number 2. So state number 2 is an accepting state with a skip self loop that allows us to basically, as I said earlier, pick any future cursor to skip to, and we will pick cursor number 6, which is the last cursor, and that puts us again in an accepting state with the last cursor of the string, so we accept. And then we go to state number 3, which points, cursor 2 points at B. We will consume the B. And then we bump the cursor by 1. We're at cursor position 3. And again, we can pick cursor number 6. And then we see here we have 3 check marks because all 3 children coming off of state 0 at this point have accepted. So that means the whole SAFA is accepted and the regex matches the string. So next we need to encode the SAFA as a lookup argument. And Jess will tell you exactly how we do that.
Okay, so we need to now represent our SAFAs in our R1CS instance, which is our arithmetic circuit. And so we do that by using lookup arguments. And what lookup arguments do is it's a primitive that's essentially a way to prove that some set of values, V1 through Vm, are in a particular table T. So in the case of Reef, we have 2 tables. We have our private document table, where we have all the indices and all the characters that are in the document. And by private table, I, of course, just mean a commitment to this table, right? And then we have a public SAFA table that's deterministically derivable from the regex by both the prover and the verifier. And this table represents all the edges in the SAFA. So all the entries are, you know, the state that an edge starts on, the character for that edge, and the state that that edge ends on. And this replaces our delta function. And so we transition through the SAFA in our circuit by proving that each edge we take is indeed a valid edge in our table, and that the corresponding character for that edge is at the correct cursor position in our document table. And so to understand how we get a little bit of extra efficiency out of lookup arguments, we should first talk a little bit about recursive proof systems. So if you are familiar with the cryptographic literature in this space, this is also called IVC, or incrementally verifiable computation. We're going to use the word recursive because it's a little more intuitive, and because the NOVA paper uses that word and we use the NOVA system. So recursive proof systems are where some prover, you know, wants to prove some function foo multiple times. And so the prover takes the R1CS instance representing foo, and it produces nodes for a single correct execution of foo. And so proving a single step isn't that useful. You can do that without a recursive proof system. But with a recursive proof system, you are able to prove then that some prior proof, pi 0 in this case, verifies correctly, in addition to proving another execution of foo. And so you can do this in a chain as many times as you want for as many iterations. And then the verifier only needs to see and verify the final proof, in this case, pi j minus 1. And this establishes in like a domino fashion that all the prior proofs were correctly verifiable, and so that all the prior foo executions are verifiable. And this helps with our unfolding the delta function problem that we saw before. So now we can only do, within each circuit, we only have to do one delta or a small batch of deltas. And the circuit size and therefore verifier time is parameterized by a single iteration instead of j iterations of something, which is ideal. I'm checking for questions. Are we good? So
yeah, we're all good. Keep on going. Thanks. This is great.
So we use a particular lookup argument called nlookup. It was designed specifically for recursive proof systems. And the way nlookup works is we have some table, and we represent our table as a multilinear polynomial t, such that t evaluated at a particular index produces the value in the table at that index. So in this running DNA example, t at 0 is character A, t at 1 is character C, so on and so forth. And the way nlookup works is it applies the sum check protocol to reduce some set of m lookups, which are just evaluations of t, to a single evaluation of t at a random point. And if you're familiar with the zk space, you probably know what sum check is. And if you're not, that's totally fine. You can treat it as a black box. What's important to know is that it takes m log t time to make this reduction for m lookups, and then t time to do this final check, which is the final evaluation of t at a random. Okay, so as we talked about, we're going to be using a recursive proof system. So we're going to be doing batches of lookups. We'll do the first proof, we'll do, 10 lookups. Then the second proof, we'll do the next 10 lookups. And in Reef's case, this will be like, the first 10 characters in the document and the next 10 characters in the document, and so on and so forth. So you'll end up with something that looks like this, where we have these batches. Question. How is the polynomial T multilinear? That is a great question. It's a little bit in the weeds, which is why we didn't include it. But basically what you do is you create a multilinear. So, you can represent a table as a polynomial pretty easily, where you just say like, okay, 0A is 1 point, 1B is the next point, 2C is the next point, so on and so forth. And then you can create a multilinear extension of that polynomial, where essentially the index, instead of being like a single field element, like 2, is now a binary representation of that field element. So like, 0, 1, 0 is index 2. And so it's parameterized by L variables, L being log2 size of table. Does that make sense? Do you use a binary field and its extensions? We use a regular prime field because then all the binary elements are representations in the table. So if you evaluate T on 0, 0, 0, you get the thing at index 0. But you can also evaluate it on T of a random point, 17, 319, and it gives you a value that's not in the table, but consistent with the polynomial. Got it. Thanks. Awesome. Good question. Okay, so we have these batches where, in round 1, I do M lookups. I reduce them to a single claim. T of R1 equals V prime 1. In the next round 2, I do M new lookups that are different from the first round, reduce them to a new claim, T of R2 at V prime 2. So on. And so this is not the best runtime we could get because you'll notice that we're doing, the reduction work per round, and we're doing an evaluation of T every round. And that T is big because the table can be very big. And so we'd like to get rid of that if possible. And you'll notice that each of these claims we have at the end, T of R1, V prime 1, are themselves just evaluations on T. They're evaluations of this polynomial. So they're actually like lookups in and of themselves. So what we can do is we can roll each lookup into the next round. So, after round 1, we have this claim about T of R1 equals V prime 1, and we roll that into the next round of lookups during round 2. And then we roll round 2's lookup into the next round of lookups at R3. And so now we only have the only T we actually have to evaluate is the final check. So in this like 3-round little example, it would just be T of R3, the last thing we have to evaluate. We only have to do it once. And so this allows us to reduce all lookups over our whole recursive proof system to a single polynomial evaluation, which is very cool. It means that as the number of lookups increases, the cost per lookup decreases. And B, it allows us to move this final T evaluation outside the proof system, right? So now our circuit can just be parameterized by this M log T reduction, and the verifier checks that once, and then this T is moved outside the proof system. So in the case of like SAFA tables, since the SAFA table is public, this can be done totally in the clear without any sort of cryptographic machinery, which is really nice. In the case of the document table, we have to do it against a document commitment. So you have to commit to the document with a commitment that allows polynomial evaluation, like inner product argument. But that saves us a lot of time. Okay, now we're going to talk about optimizations that we do on top of NLOOKUP. Up until now, we've been talking about the complexity of our R1CS instance, our circuit, and therefore the verifiers work to verify the proof, and the verifiers work to do this final check. But it's also important to talk about the prover's work to produce the witnesses for the NLOOKUP instances in our circuit. And so because the prover uses, because we use sum check within NLOOKUP, the prover has to compute over the whole table to compute the sum check witnesses every round. So this means that the prover does T work for each iteration. Excuse me. which is not ideal, especially in cases like DNA, where the table might be much, much bigger than the actual lookups we do. We might only do lookups because our SAVs allow us to only do lookups over, the stuff that's related to the regex. We might have this whole chromosome and this very small gene. And so then the prover's doing work over the whole chromosome each time, which gets out of hand very quickly. So in this example that I have over here on the right, you'll notice these lookups only come from the bottom half of the table. We have this T110, which is, of course, T at 5, because all these are in binary. The T at 5 is A. We have T at 7 is G. And so these only come from the bottom half of the table, so it's a waste of time to do computation over the whole table. So what we do is we allow the prover to pretend that only this bottom half of the table exists and just do his computations over this bottom half of the table. And we call this process projecting onto a particular subtable. And so now our lookups look like this, where as far as the prover is concerned, this A lookup is at index 0 instead of index 5, because the first half of the table doesn't exist. And so now the prover's time is parameterized by this new table, T1, which is half the size of the original table. It's important to note here that the verifier's time improves a little bit, not that much. The verifier still has to do this final check over the original table, A, so that it can make sure the prover isn't doing anything funny, and B, it's so that we don't have to change our commitment, because there might be situations in which we want to commit to, a genome and then prove multiple things about it with different regexes, which maybe have different projections. So the verifier makes this final check against the original table. So we don't have to change the commitment. So you might be wondering, does this method generalize to multiple projections? And it does. So you might imagine a situation like this, where we have, we have these lookups from this first fourth of the table, and then we have some other set of lookups from the third fourth of the table. And so the most, straightforward naive solution would be you could have 2 nlookup instances in your rank 1, in your R1CS instance. And you could have 2 sets of lookups, and the prover computes lookups over table 1 or table 2. And this is more efficient than the prover doing lookups over the whole original table. But you have to have extra circuitry to distinguish your lookups, and it is a mess. So what we do is we allow the prover to actually combine these 2 tables. He pretends this is just one table and gives it a new structure where he says, okay, this first chunk is going to be chunk 0. The second chunk is going to be chunk 1. And so this is what the prover sees. And so now our lookups have to look a little different. G is at index 0, 0. A is at index 0, 1. And this is fine. This is great. It allows us to do 1 nlookup instance, have 1 running claim. It allows the prover to pretend that this small table is all that exists. He doesn't have to understand that there's multiple tables happening. Again, we have to structure our final check to correspond to the original table structure, which is this green column here. The verifier has to sort of understand where these chunks came from so he can understand how to check them against the original commitment. So in this final check, the prover says, like, okay, my final claim about my hybrid table that I have is about this point R0, R1. And so R0 sort of tells the verifier to select, like, okay, which original chunk did this come from? Then R1 indexes into the actual table. And then the prover has to provide this original structure information, this T00 and T10 that tell us how the chunks relate to the original document commitment. And so this generalizes to any number of disjoint chunks in the table. In fact, you can even have chunks from different tables. And in that case, the verifier would say, like, okay, so this first chunk comes from table T at T00, and this second chunk comes from a different table, table F at F10. And that's totally fine. That works out. In fact, you can even have one of these tables be public, like our SAFA table, and one of them be private, like the document table. And as long as the verifier does some bookkeeping and he knows where these things are coming from, he can perform this final check half against the commitment and half in the clear, which is really nice because it means we can combine our public SAFA table and our private document table into just one table. So there's just one nlookup in the circuit. So to summarize, We talked about document projections, which run over subsets of our larger document table. In its most straightforward setting, we talked about public prescribed offsets, which means the prover and the verifier agree, like, all right, we're projecting over this chunk of the table, which works when the regex has a prescribed offset. And we know, okay, how much of the document can we ignore? It doesn't work when you have something like cleaning star like this regex, because then saying, oh, well, I'm projecting over this part of the table leaks something about the document. There is a way to hide the projections, and there is a way to hide the document length with similar optimizations. And we talk about that in the paper. And then we talked about hybrid tables, where you take projections from different tables, which can include, the full table maybe, and you combine them into a single table, which makes the prover and the verifier work better, because the prover only has to do, you can pretend everything's one table, and the verifier only has to have one and lookup instance in the circuit. As long as the document or the part of the document you're projecting over and the SAPA table are close in size, close being 3 orders of magnitude, this will give us savings.
I have a question real quick. Can you describe again just the document projections concept? So, if I'm thinking about this in terms of a regex, pattern that I want to run against a document, the projection can be thought of as just the portion of the SAPA table that I care about, I guess, with regard to the regex. Like, explain one more time the concept of projections. I think I'm a little confused.
Yeah, no, you're good. Think of projections most of the time. All right, in terms of the SAFA table, most of the time we're going to want the full SAFA table.
The full table, right? Because that's your actual pattern, right? The SAFA table is your pattern that you're searching.
Yeah, that's the actual SAF. That's the actual graph with the nodes.
So this optimization would not apply there.
No, unless you can, because if I was to say to you, I only care about this half of the SAFA, then why do I have this other part?
You wrote too much of you wrote a pattern that was too long, right? Yeah,
exactly. Yeah. So most of the projections just apply to the document table. And so it's basically saying all right, I know that, maybe only this half of the document I'm going to look up. Maybe the first part of the document is all wildcards, so I'm never going to make those lookups. So why do I need to include that in my computation?
I see. Okay, so if you have some knowledge about the structure of the document beforehand, you could potentially apply an optimization like this, right? Because it's real. Because I guess the question that comes over my head is if you, let's just say naively say, I'm only searching the second half of the document. What if the regex pattern would actually match if you had looked at the character immediately before the second half, right? You know what I mean? So I guess you just basically have to know that you're foregoing searching effectively the first half of the document. Is that, or are you just assuming it will always match? Like in the case of this clean star thing, you're like, okay, whatever, this is all going to match anyway. I know the A's start in the second half. Sorry, does this question make sense? I think that's it.
Yes, this question makes sense. Okay. It's a good question. You don't have to know anything about the structure of the document. What you have to know is you have to understand the structure of the regex. Like in this first example here, this 10 wildcard ABC.
And this is, if I guess, just reading this regex, I think for those who might not be familiar with notation, I believe this is 1 or 0. No, this is 10, right? This is 10. Collectively, right? And then ABC, anything. So anything plus 10. ABC anything, right? And it's anything in the first regex is one instance of anything, right? The dot, right? Any character.
Yes.
Great. Sorry, I just wanted to, for those who are not regex fluent, I just wanted to say that out loud. Go ahead.
No, I appreciate that. We've been looking at these for years, so it doesn't always occur to me to say that. So in this case, I know no matter what the document is, I know we will never care about those first 10 characters. So I can project past those 10 characters. In this,
I see.
In this second example, because there's a dot star, I can't use projections because I actually don't know where the A is going to start without leaking something about the document. So it wouldn't work in this second example.
I see. Okay, so sorry, and let me restate for the purposes of the recording because I said something wrong earlier about the reading of this regex. The first one is any character 10 times. Right. And I think it has to be, so it's 10 of any character. right? So you're always going to match the first 10 characters no matter what they are, right?
Yes.
And but the length of that is bounded by 10, right? It's 10. You're saying it's 10. Whereas and you're saying it wouldn't work in the first case because in the second case is because that character, the clean star, is matching any number of times, right? 0 or more. So that in that case, it could be 1, it could be 10, it could be 100 instances, and so therefore you don't actually know where to offset is fundamentally the idea here. Is that right?
Yes.
That
Okay,
is great.
correct.
Thank you.
Good.
Any other questions? Cool. All right, great. So now I'm going to talk a little bit about how we evaluated Reef and how it compares to existing systems and protocols. So to evaluate Reef, we looked at a wide variety of questions. These aren't even all of them. And I don't have time to cover everything. So I'm going to focus on this subset. Can Reef support a variety of regexes and document sizes? Is it efficient for the prover? How does it compare to existing and alternate solutions? And what impact do the additional optimizations, so the projections and the hybrid tables, what impact do they have on performance? So Reef supports more robust regexes with fewer constraints than existing systems. So at the time that we publish, there were essentially 4 other systems looking to do something similar. Zombie, which is zero knowledge middle boxes, zkRegex and zkEmail. All 3 of these do, full regex matching minus, lookarounds. And then there's zkReg, which does fixed string matching for regular languages. So you'll see here, Reef supports everything all of these systems do, as well as lookarounds. And not only does it support everything these systems do, but it does so with fewer constraints. So you'll notice that Zombie, zkRegex, and zkEmail are all kind of the form, size of document times at least size of automata, which is, right, not great. And we had talked about this earlier on. Reef, however, not only do we make that additive, so size of document plus size of automata, but we push all of it inside a log, right? So it's a pretty significant reduction. Additionally, you'll notice Reef has this alpha at the beginning. This is the number of lookups that we have to perform. And this is defined entirely by the regex itself. This is not defined by the document. It's document independent. So we're able to kind of have a number of constraints that's really pretty independent of the document. The 4th system, zkReg, does have sort of an additive number of constraints, right? So size of document plus size of automata, but they use something called an Aho-Korosik DFA, which tends to be, multiple orders of magnitude larger than SAFAs. So this is all theory. Theory is great, but what about practice? So
sorry,
we evaluate.
Eli, can I just interrupt you quickly? Can you go back? I guess just for folks who are watching this video who may not be all familiar with these acronyms, like NFA is non-deterministic finite automata,
Yes,
and DFA is deterministic, right?
Yeah, so TNFA is something called a Thompson non-deterministic finite automata. It's what a lot of sort of regular expression matching engines use under the hood. And ACDFA stands for an Aho-Korosik deterministic finite automata.
Thank you.
Sorry about that. So we evaluate Reef against 4 applications, proving things about large and small redacted documents for Freedom of Information Act requests, oblivious DNS over HTTPS block listing, proving strong password matching and non-matching, and then proving matching and non-matching for specific genetic mutations. So this covers a wide range of document sizes, going from 6 characters to 43 million, and a wide range of SAFA sizes as well. So we have some very small SAFAs, meaning, those with 16 states and less than 2,000 transitions, to some very, very large ones, which are, almost 1,000 states and over 100,000 transitions. So we try to cover a pretty wide range in what we test. So in order to test Reef, we look at 3 baselines. And we do this because at the time that we were doing Reef, there wasn't publicly available source code that we could easily compare against for the existing works. So instead, we consider 3 baselines. The first is just kind of the classic DFA or deterministic finite automata that we talked about at the beginning. So representing a delta function with a bunch of if statements and then just iterating through it with a for loop. And you'll notice there's a lot of X's in this column. And that's because even with a machine with 712 gigs of RAM, we couldn't compile the circuit. The circuit was too big to compile in all of the cases with X's. In the 2 cases that we could compile it, you'll notice it's, well over 1 million constraints.
And sorry,
The next
Eli,
thing we look at-
sorry, quick question again for me is when you said documented redaction large means the document is large or the redaction is large?
The document is large.
Okay, got it. Thanks.
Yeah, no worries. And so next we looked at replacing that for loop, that sort of traditional for loop, with a recursive proof system. So again, we're going to have a delta function that's a bunch of if statements, but now we only have to instantiate it once in the circuit, and we can use a recursive proof system to iterate through the document. And you'll notice that there are still some X's here, but we're doing better. We can represent the first 3 examples with orders of magnitude fewer constraints. So it's progress. Next, we compare to kind of the core of Reef, which is going to be the use of lookup arguments and SAFAs. We can now represent everything efficiently. And again, we get a pretty big reduction in the number of constraints, anywhere from 2,000 to almost 100,000. And then the final thing we look at is Reef. So this is going to be the SAFAs plus the lookups and the optimizations that Jess described. So the use of hybrid public-private tables and the use of projections. And you'll see here again, the number of constraints goes down, but it doesn't go down that much. So you might say, okay, well, what is the benefit then of these optimizations? Well, the benefits really come into practice when we look at total prover time. So here we have the document redactions example, both the small and large one, and the DNA matching and non-matching. So let's start with the document redactions. Here we have the SAFA plus lookup for the small case, and the SAFA plus lookup and Reef for the large document redactions case. You'll notice right away that Reef and the SAFA plus lookup application are multiple orders of magnitude faster than the alternative. One obvious question that you might have is that, okay, but the circuit size in the DFA plus recursion case wasn't that much bigger. Why is it so slow? That's because even in the DFA plus recursion case, you still have to go through every single character in the document. Whereas by using SAFAs, we can eliminate a lot of that work. We have to do significantly fewer number of iterations. So here, SAFA plus lookup and Reef perform about the same. So the optimizations, though, really shine in cases like the DNA matching and non-matching case, where here we have Reef versus the SAFA plus lookup. You'll notice that Reef is, again, pretty fast. It's much faster also than the SAFA plus lookup. And that's because, right, in this case, the DNA chromosome that we're looking at is 43 million characters long. By using projections, we avoid having to do operations over the entirety of that table. We save a lot of work. So in the matching case, it's about an order of magnitude faster. And in the non-matching case, it's about an order of magnitude faster. And in the non-matching case, it's about 3 orders of magnitude faster. Sorry, let me see. I see a question in the chat. Sorry if I missed this earlier. SAFA allows skipping all characters that can be wildcards not relevant to the match. Yes, that is the key insight of SAFA is that for wildcards, we don't actually care what the value is. It just has to exist. So the takeaway here is that even without Reef's additional optimizations, the key insights of Reef, of the SAFAs and the use of lookup arguments results in order of magnitude faster prover time than alternate solutions. So in summary, we want succinct zero-knowledge proofs for a variety of regexes that scale well for large documents. We can use SAFAs to get better expressivity and skip irrelevant parts of the document, and we can use lookup table for document commitment and SAFA transitions, which gives us Reef, which has support for a variety of applications with fast prover and verifier times and fewer constraints than alternatives. So I want to now I know people have been asking questions in the chat, but I want to open it up to kind of questions more broadly from anyone.
Super cool. I have a couple more questions if no one else wants to jump in. Okay, can you go back to the comparison slide?
Yes, sorry, I don't know what I just did.
All good.
Let's all right, let's see what's happening. All right, can you guys still see the slides? Yes, hopefully.
Yeah. Yep.
Great.
Yep. Okay. And yeah, for these comparisons, these concrete kind of, comparisons, I was just curious, what is the size of pattern and what is the size of document? I know you mentioned in the DNA case, it's 43 million characters, but yeah, maybe you already had this here, but okay, got it.
Yeah.
Okay, got it. Document sizes.
Well,
And then what's the size of the pattern, I guess, right? Because that would affect the lookup table, right?
yeah, so we represent the size of the pattern in terms of number of states in the automata.
Yeah. Oh, I
and I'm
see. So
showing,
so SAFA states is effectively the size of the pattern, or is correlated with the size of the
exactly.
pattern. Okay, got it.
I would say it's more accurate to say that the SAFA transitions is correlated with the size of the lookup table because the lookup table is made up of the transitions.
Got it. Okay. So roughly speaking, you can think of like the size of like if a larger pattern is more transitions, smaller pattern is fewer transitions.
Yeah, and then I think
Great.
let me double check really quickly. We have in the paper the equivalent number of states and transitions for the DFA representation or NFA representation as well. And in some cases it's smaller, or in some cases it's about the same. I'm sorry, it's never smaller. In some cases it's about the same, like in the redactions case, whereas in the DNA case it's about 4 orders of magnitude larger.
Yeah. Cool. Go ahead, Pratyush.
Yeah. Thanks for the great talk, you guys. I've been asking some questions in the chat, but I thought I'd just say hi and also ask a few more questions that I have. So the first one is, so if you could go to the concrete security, no, not the concrete security, the asymptotic security, not security efficiency slides. This one, yeah. So I see this alpha value. So is it possible that like if the document is really small, I don't know exactly what the alpha value is, that some other solutions might still be better for a small enough document?
So the alpha value here is defined primarily by the regex, not by the document. Okay. So like what you can get is if the document and the regex are the exact same, right? If I have the document ABCD and my regex is literally ABCD, then alpha is the size of the document. Right. And so in the worst case, I think asymptotically, in the absolute worst case, you could construct an adversarial regex where alpha is on the order of the size of the document. But otherwise, it's going to always be smaller than the size of the document.
Yeah.
Why is it adversarial though? It doesn't, it's just like check, right? Like it's not necessarily adversarial.
Sure. I guess if you wanted, I guess by say adversarial, I mean like kind of like worst, if you wanted to construct a worst case.
Yeah. Okay.
The worst case, and this is, if you read the paper, this is we have a calculation for alpha in the paper that's the worst case. And in the worst case, you have a regex that's all look-aheads, and every look-ahead is an exact document match. And so alpha is document size times number of look-aheads.
Yeah, and I guess like if that's the case, you should probably use like an exact matching scheme. Like those are like, like a cryptographic matching algorithm instead of like doing all of this. Cool. The second question I have is, have you tried comparing this? So for like the TLS attestation protocols, like, I don't know if you guys have seen those. This problem occurs quite a bit, right? You have TLS attestation protocols. There's a notary that says that this is a valid TLS ciphertext. They saw it online and they open like some of the plain text inside it, or say like, this string occurred at this position. I guess similar to zk email. So I couldn't really map from the comparisons you had how it would compare to these other approaches like zk email. Like if you were to do the zk email thing, like how much more efficient would it be?
Yeah, so I think when you're talking about the like TLS attestation, you're talking about like the DECO protocol.
Yeah.
Okay.
DECO and other similar ones.
Yeah. So in terms of like zk email, so zk email actually is more or less what we implemented when we talk about that like DFA baseline that we compared against. That's essentially pretty much exactly the same thing that zk email does.
Got it.
And so, right, performance-wise, Reef is much more efficient for that. For DECO and some of these like TLS attestation protocols, they do something a little bit different. It's not clear exactly whether or not Reef would be better or worse. In this case,
I see. Let me make it more particular then, right? So like one example of like an implementation that does this sort of regex for TLS attestations is they take this whole string that's the entire TLS session. They take all the parts that are not relevant or like you don't want to prove things about, and you replace those with stars. So then it's like a bunch of stars, and then the things that you want to show are in like the same position. So for that case, like what would be the order of magnitude improvement?
Yeah, so that's pretty much exactly what we do in the document redaction case. So,
Okay,
right,
cool.
that is exactly what we do in the document redaction case, because redacted government documents are the same thing as you have a document, and the parts that you need to redact, you dot star. So you would expect that, you know, Reef would be much faster because we can skip those dot stars.
Makes
A
sense.
thing that comes up with a TLS attestation, and this might be a different issue, is that you kind of are trusting that a lot of times that these JSONs are properly formatted, which is a different set of problems entirely. Confirming that they're properly formatted is a whole other nightmare.
Yeah, fair enough. And I guess one final question is, looks like you guys have a lot of improvement over many protocols. So what is left for future work, right? Like what is the juice, so to speak, left to squeeze, if any?
Yeah, so there's a couple. So one of them is like we kind of just mentioned, that like with TLS attestation, checking that things are properly formatted is a similar but whole other nightmare. So seeing whether we can adapt some of the techniques there. We're also looking at using Reef for a number of other applications that are a little bit more complicated than just straight regex matching. I don't know, Jess, if you want to talk about your compiler work at all.
Yeah, like essentially, like, you know, the insights from Reef that like you only need to look at the things you need to look at, and lookup tables are faster than computation, which is, you know, not a new idea in this space, but a good insight can be applied to a lot of other things. Yeah, I'm working on proving stuff about compilation passes in zero knowledge, where you have some like AST and you prove transformations on it. Yeah.
Cool. Yeah, I think I just want to understand the JSON formatting issue clearly again. So like a JSON file is a very specific structure, right? So is the question that it is formatted as a valid JSON file, or is it something else?
Yeah. So to get, depending on how in the weeds people care to get about this. So, right, regular expressions describe in like academic theory land something called regular languages, right? Which for something like JSON, you can use something called a context-free grammar, which describes a context-free language, which is kind of a superset of regular expressions. And so when you're checking that a JSON is properly formatted, or that a string has balanced parentheses, or that XML is validly done, that's called that's context-free grammar checking, which is like regex checking and has a very similar flavor, but is unfortunately significantly more complicated.
So is one the subset of the other?
Yeah, regex is a subset of context-free.
Sounds good. Okay, awesome. Thanks a lot. And thanks, Alex, for organizing these. I enjoy them a lot.
Yeah, no problem. Yeah, big thanks to the authors. And I had a couple more questions too. But thank you for your questions, Pratish. So one question I had is, in your guys' scheme, I know there's some differentiation between different regex engines on how to handle lazy and greedy quantifiers, right? Like depending on the engine, like you might be satisfied that you found a match. Let's say like the number one, where it's like, do you stop at one if it's one, if it's curly brace 1, comma 2 curly brace, do you stop when you find 1, or do you keep looking until you find to see if there's matches that also have 2, right? So this concept of like a lazy versus greedy quantifier, I guess, how do you guys handle those here? Is that, if you could just make, comment on that, would be great.
So I think the answer is non-determinism is sort of a superset of those two. And we use non-deterministic witnesses. In fact, I think in the example that we showed of Safa matching a string, there were multiple solutions, and we non-deterministically picked one of them. So I guess maybe the answer to your question is we don't make a choice. We leave it to the prover.
Got it. So as long as it's valid, the prover can pick any of them.
As long as it's valid, the prover will, yeah, exactly.
Got it. Got it. So I guess though, this maybe is like a hair splitting point, but it's kind of interesting, right? Because I guess effectively it depends, like for a document redaction case, this could possibly come up, right? Because there's two instances of the same string and you're basically quantifying you found all of them. You could get away with just saying you found one of them, but there's still one more, right? As a prover, would this be a real world consideration?
Yeah, so I think it is.
I guess you'd have to quantify basically what you want. Let's just say you wanted to redact my name from a document, right? You'd basically have to figure out a way to make the greediest quantifier. You'd have to quantify it as greedy as possible, right? And I guess just figure out how to do that. That's just probably just a matter of writing the pattern.
Yeah, what we did is we essentially replaced. We took like a leaked documents database and essentially did that. And every time we saw like kind of a PII, we replaced it with a dot star. So you still have a kind of enough text surrounding the dot stars that you kind of have to go through the entire thing. Like you can't really cheat with that. But that is like a big thing, is if you're redacting, you know, the entire document and the only thing unredacted is like the word "the," you could maybe run into some messiness there.
Yeah, I guess I'm just thinking in the case you guys described, you were the prover, but if you had an adversarial prover, right, you basically are like, hey, redact everything for me, prove that you did. And I said I did. But did I, you know, I guess it just kind of, this is where this question would come up, right? Like, did you actually find all the instances and then redact them? Or did you only show me 4 of the 5 and say you did, right? And I guess would the statement still, would the verifier still accept that?
Yeah,
I think what Alex is talking about is kind of the opposite of match. It's kind of, I want to prove that my name does not exist. It's kind of the negation, right? And in the negation case, we like you said, we have to go through and check every part of the document. There is no way around this.
Yeah.
I think when we were doing the document redaction case, we were kind of thinking more along the lines of not proving that you correctly redacted a document, but proving that, you know, let's say I'm a journalist, I submit a FOIA request, right? Proving that, you know, having the government prove to you that there is some real underlying document that relates to this redacted document that's been published.
Got it. Okay, cool. Well, that's super helpful and very clarifying. Thank you. Yeah, I think that was maybe my last question. Does anyone else on the call here have questions? Pratyush, Bettina, anyone else?
I'm all good. Thanks.
Cool. Oh, I did actually have one more question. I lied. Can you provide a reference for the end lookup protocol? I'm actually not familiar with that, and I've not seen it before. So if you guys could just share a reference either in the chat or yeah, send it to me and I'll put it in the show notes or in the description.
Yes. I will send it to you and you can put it in the description. I will also mention that this end lookup protocol is described by Srinath in the Hypernova paper.
Got it. Okay, cool. All right. Awesome. Well, thank you guys very much. I really appreciate you coming on today. Last call for questions. Anyone have questions for the authors here today? All right. Thank you guys so much for being here. Really appreciate it. This was a great session. And for those folks who are, tuning in, we'll have another session coming up in a couple of weeks. We'll be announcing more about that in our channel, and you should be expected to see this video up on YouTube here very shortly. Thank you guys very much.
Thanks so much.